of eye tracking for continuous authentication in virtual reality. So, to talk about the authors of the paper, I'm Sai Ganesh Grandhi. I'm a grad student at University of Windsor, and my professor and my supervisor, Dr. Samet, and I wrote the paper. And my professor couldn't able to attend the meeting today, so I'll be uh, presenting the topic today. So let's first talk about eye tracking. So eye tracking is the study of uh, measuring the eye movements. It's it studies features such as saccades, fixations, microsaccades, and these eye tracking features are collected by XYZ coordinates of eye position, and there are also other features such as microsaccades and others. And these features are collected in time series format. So whenever our eyes are moving in a virtual reality headset, our eye positions are collected in time series format of XYZ coordinates, and these these are collected in milliseconds according to the headset's uh, refresh rate. If a headset's refresh rate is 250 hertz, then we can collect 250 timestamps per second. So the main eye tracking moments are saccades and fixations. A saccade is a moment between 2 points and 2 points of an eye, and a fixation is a single fixated point of an eye. Uh, so these two are the main features of eye tracking, which are used to uh, you know identify a user. So what what we tried to do in this research is we tried using eye movements to identify users. So these kind of uh, movements of a body is called behavioral biometrics. Behavioral biometrics can be from your gait, from your touch, from your eye movements, or from your head movements. So as you can see on the table, there are these are the types of behavioral biometrics. So using mobile devices, we can track gait movements and touch patterns, and using VR headsets, we can track eye movements and head movements. So what is continuous authentication? Continuous authentication simply authenticates you throughout the session, throughout the login session, using your behavioral biometrics. In our case, it's eye tracking. We used eye tracking to uh, verify users' identity. It can be used as a multi-factor authentication. Uh, it can be paired with physical biometrics such as iris and fingerprints. It doesn't require any users' inputs, like users don't need to provide any passwords. It users can be verified in the background. So with VR headsets, there is a problem with static authentication. Static authentication is is your typical password and pins. Uh, it, it it disrupts your VR experience, and it also is prone to shoulder surfing attacks, which is when you are typing your password in the air, a user can guess your password by looking at you repeatedly. So, and it also provides dynamic authentication. So you cannot steal any tokens or passwords or anything from a user to log into the session. So continuous authentication has evolved from desktops and mobiles to VR headsets now. The problem with uh, desktops and mobile phones is that you cannot take a lot of behavioral biometrics from your mobile phones. For example, when you are collecting gate information, you can only collect when the user is in the moment. When the user is stationary, uh, we cannot collect behavioral biometrics. But in the case of VR, eye movement is very easy to collect from the user because user is continuously moving their eyes, and we can collect the user's eye movements in the VR. For VR, it's a very good uh, it's a very good application uh, to collect eye tracking and use it for continuous authentication. So how does this architecture work? Is it simply has two phases. One is registration phase and another one is authentication phase. Uh, so in registration phase, the user uh, tries to do some tasks, and then uh, data is collected, and then an authentication model is built on that. And during authentication phase, uh, the eye tracking data will be collected when the user is using the VR headset, and it is authenticated using the user behavioral user model, and then we will classify it as a right user or wrong user. So there are advantages and disadvantages of eye tracking as a continuous authentication. It prevents session hijacking. It provides seamless user experience, and it can be used as MFA. On, at the same time, it also has disadvantages. Users' behavioral patterns change over time, so you need to continuously update their behavioral patterns over time, and it cannot function as a cross-platform authentication. And also, there are a lot of privacy concerns regarding continuous authentication because you are collecting users' sensitive data, which is eye tracking. Many users might not like collecting their eye movements and using it for authentication or whatever purposes the organization might use. So whenever any organization uses these kinds of data, there should be some adherence to privacy laws, and they should be fully transparent of the organizations should be fully transparent of how they are using the sensitive data. So our study was uh, motivated from an existing continuous authentication study by uh, Lore et al. 2022. They created they created a framework called I know you too using DenseNet architecture, but we used Transformer Encoder architecture, and we wanted to see if it gives any better performance compared to DenseNet architecture. Also, we tried to we tried to see how transformer architecture works in long-term identification of users. So I will discuss about the long-term identification of users in the upcoming slides. And we also uh, compared our efficiency of transformers and DenseNet architectures. So we used transformer encoder architecture. It uses self-attention mechanism. We only used transformer encoder architecture. We did not use decoder architecture in this. It is inspired from the original Attention is All You Need paper, and we only used encoder because this is a classification problem and this is not a text generation problems. So we only try to use encoder, and then we after after encoder is completed, we use a softmax layer to classify the user. And to perform this study, we used GazebaseVR dataset. This is a very big open source dataset which includes 407 participants, and it is performed in 26 months of time span. So it is captured using 3 rounds, and it has a 250 hertz sampling ratio, and it's a binocular data set. So if you break down the GazeBase VR dataset, there are 5 tasks in the dataset. I mean, the participants performed 5 tasks in this. These are jumps, smooth pursuit, video, viewing, reading, and random circuit tasks. Each task tries to capture different kinds of eye movements. And also to compare our transformer architecture model, we also employ a DenseNet architecture and XGBoost architectures. XGBoost is because we wanted to see how less computational machine learning algorithm will perform with transformer, because transformer is a very computationally heavy model, and also DenseNet is a deep convolution neural network, and there is a research already done using this architecture. So we use these 2 models to compare our transformer model. So we split it into 80-20 ratio, and then we used 5-fold cross validation. We set the learning rate at 0.001, and the epoch size is at 50 rounds. As I told, it is inspired from original transformer model. It has 4 encoder layers and 8 attention heads. It has a feed-forward network of 64 and dropout rate at 0.1. And we used features of 6 spatial coordinates, which are XYZ coordinates of right and left eyes and timestamps, and the user IDs of each ID. Then we normalize the data between -1 and 1. Then we use the windowing size of 5 seconds, and then uh, uh, we try to train the model. We train the model, and this training has been set up on performed on Compute Canada resources. As you can see, we used various CPUs and GPUs to train the models. So, uh, so our model has performed pretty well compared to XGBoost, and it also outperformed DenseNet architecture. Uh, you might think that this is a small difference, but in authentication standards, even zero point 0.5 terms of zero point 0.5 increase in accuracy is also very good. We have to reach 99%. Uh, I hope in future this reaches to 99.9% so that it can be deployed in the real world scenarios. And individual tasks, if you see, divergence task has outperformed all the tasks, and smooth pursuit task has also uh, good results. This is because Virgin's smooth pursuit and random saccade tasks have a lot of eye movements compared to video and text tasks. So we were able to capture a lot of we were able to capture more accuracy using these tasks. But if you look at neural network versus machine learning, like I said, XGBoost versus Transformer architecture, uh, XGBoost got lower accuracy. So we saw that there is a trade-off between accuracy and computational efficiency. So the more heavier the model is, the better accuracy we are achieving. But this will be very difficult in real world scenarios because eye tracking headsets might not be able to take these kind of loads from transformer architectures. But we still have to, there is the research has to be done in that field in the future. In the future, so uh, long-term user identification is basically we try to identify a user using in 26 months period of gap. Like uh, we want to test a user by collecting the user's data from this day and then testing the user after 26 months. So we want to see how eye tracking works in long term because uh, because if fingerprint doesn't change or your iris pattern doesn't change, but behavioral biometrics is a data, so it changes periodically. So we wanted to see how it performs in long term. So that's why we chose this data set which has 3 rounds of data that is collected over 26 uh, months of span. So we trained the model using round one data, and then we tested the model using round three data. And the results we got is we got a very less accuracy when we did this. So these are short-term results. As you can see, the training and testing rounds are same rounds. That means uh, they both were collected at the same time. So these were pretty good accuracy scores. We got 97% and 79% using XGBoost. But when we went into long-term results, when we tried to uh, test the user by uh, you know mm, training the model using round one data and then testing the users using round three data, which is 26 months afterwards. And then we saw an accuracy reduction by 80 to 90%. That is, using transformers, we got very less accuracy. Using DenseNet, we got good accuracy of 7.79%, but that is not a good thing. But when we But when we mixed uh, round 3 data into the training data, we we saw increase in the accuracy uh, of the user prediction. We again got 98% data. So, but we did not mix and match the testing, and we split the data into equal parts. We split the round 3 data into equal parts, and we combined it one part into the training data, and we tested the other part in uh, testing data. So this made us realize that there needs to be a continuous updation of user uh, behavioral biometric data when there is over long period of time, when we are dealing with behavioral biometrics using eye tracking. And this also applies to other behavioral biometrics such as gait or hand movements or head movements. Uh, so So there are a lot of privacy concerns regarding this collection of eye tracking data, as we discussed before. It also uses mental state and physical states can also be discovered using eye tracking data, and this should not be used against their will, against a user's will. And user consent and data usage transparency should be the first place in whenever doing these kinds of research. So the key findings are uh, Transformer perform well compared to DenseNet, and then long-term challenge accuracy drops to less than 10%, and XGBoost machine learning networks perform less well than neural networks. And then in conclusion, task dependent performance, video recording and text reading perform less compared to more dynamic eye movements such as smooth pursuit. And there is a practical trade-off between computational efficiency and high accuracy. And yeah, so these are the references we used. And thank you.